Hello. Hello friends. I am going to teach stats 2 for this course, IITM BS course. Actually this is considered a very tough course. We will start from the basics and then we'll try to add on. So without any ado, I'll like to start the course. Chapter 1. Now what is we have joint, marginal and conditional of multiple discrete random variables. यहाँ पे from our previous courses we know what is joint, I don't know what is marginal, we somewhat know what is conditional. Conditional is like probability of A given B. This is the condition that B has already happened. Okay. And we also know multiple discrete random variables. So we know what is a random variable, we know what is a discrete, there are discrete and continuous. Okay, so discrete will be in integer form, this will be in a decimal form, fraction form. Discrete we have PMF, we have PDF, density function. Multiple we use like example, multiple more than one random variable. So joint, marginal, conditional for more than one discrete random variable. Okay, now let us start. We have seen previously some usual outcomes and experiments. They are quite complex in nature. There are a lot of different outcomes that is of interest to us, and lot of different random variables defined on the same probability space that are of interest to us. In the first 2 weeks we will see how to deal with multiple random variables in a probability space. One event experiment, there can be multiple random variables. Example, toss a coin thrice. A fair coin is tossed thrice, we will get 3 outcomes and naturally there can be 3 random variables. Okay, let x 1 if the ith toss is head or is tail. So basically xi becomes confusing. Simply there are 2 random x1 and x2. It is, if the first toss is head or a tail, then it will be 1, this will be 0. Second toss is a head or a tail, this will be 0, this will be 1. What this one? Ith toss, ith is belongs to 1 and 2. Ith toss is head, then 1. Ith toss is tail, then 0. So there are 2 random variables. Instead of writing this much, they have written it in a very short form. The probability space is same probability space. You can say same sample space, which tells us about all the outcomes of the event. The 3 random variables x1, x2, x3 together. Here there is a x3 also, head, tail, 1, 0. The 3 random variables x1, x2, x3 together completely describe the outcome of the experiment. The x1, x2, x3 are independent of each other. independent of each other. Why? Because like x1, whatever the result is, head or a tail, this will not influence the result of x2. Okay na, ye what is head or a tail. So this and this is independent. x2 does not depend on result of x1. This was what they are saying. Events defined using x1 alone will be independent of events defined using x2 alone, and will be independent of events defined using x3 alone. Even though all the random variables live in the same probability space, if we define events with each of the random variables separately, the events will be different and independent. Okay, defining it separately, then they are independent. Example, random 2-digit number. If 2-digit number from 00 to 99, number is from 00 to 99. There are 100 numbers. Partial information is available about the number as 2 random variables. If x be the digit in unit place, x will be digit in unit place. This is x. Let y be the remainder obtained from the number is divided by 4. So 0, 1, 2, 3. A number is divided by 4. We can get only 4 remainders. Like 1, 3, 4, 5, 6. Here numbers we divided by 4. Remainder will be 0. This remainder will be 1. This remainder 2, 3. This remainder will be 0. Then again 1. Then 2. So this only 4 numbers will get the remainder. Then that x can take any value from 0 to 9 uniformly. Okay, x can take any value from 0 to 9 uniformly. Since total number of outcomes is 100, therefore p of x equal to 0 equal to 1 by 10. Total outcomes, if we count from 0 to 9, from 00 to 99, there are total 100 numbers, and each number has 0, whether 1, 2, 4, 9, 10 unit digits. 0 for 0 we have 0, 0, 10, 20, 30 to 90 to 10. Similarly we have 0, 1, 11, 91. So we have 10 digits. Similarly for 2 we will have 0, 12, 22, 92, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 digits. So for every one there will be 10 digits. As for every unit digit there will be 10 digits. There will be 10 numbers. So the probability of having 0 is 10 divided by total. This will be 10 divided by total. Similarly so on. So 1 by 10 will be the probability of x, p of x equal to t, some number t belongs to 0 to 9. Similarly, p of x it is same, x is a uniform, so all the probability is same. We are saying that x is a uniform random variable with range from 0 to 9. We will have the remainder as 0, 1, 2, 3 for any number divided by 4. Same as the probability of 2 digits number having this will be divided in 4 parts basically, so that we'll get 20. So now there's nothing changed now. I will get 0, 1, 2, 3. So this will be 25 numbers, this will be 25, 25, 25. So all 25 numbers will divided by the total number will get the probability of y. And y will also be uniform, as we know, range 0, 1, 2, 3. And this is the same probability space. Okay, we have defined two random variables. Now suppose event x1 has occurred, it means the last digit of the number is 1. Then what about the event y equal to 0? Initially we are seeing that x1, x2 were independent. Now there can be a change in this random variables. If x1 is 1 and y equal to 0, is any number possible? With, see, these are 2-digit number, and if we divide it by 4, for division of 4 we need at least even number here. So any number that ends with 1 cannot be a multiple of 4. So the events x1 and x4 are not independent. Understood? They are not independent. We saw such things and can also happen, unlike the contrast example where any event defined using one random variable was independent of any event defined using the another random variable. Next example we will see how this play a role in modeling and other things in practice. अब IPL power play over. We will look at IPL power play over data. The experiment is 1 over of IPL over where let's define two random variables x and y. 1 over है हमारे पास, x and y random variables हैं, represents the number of runs scored in the over. Number of runs in over, or y represents the number of wickets in over. Okay, consider events y equal to 0, y equal to 1 and y equal to 2. We know that the event y equal to 0 will be the most common. And generally in an over, wickets do not fall. Like there is a 50 over match, like a 20 over match, and most of the time we'll see that 6-7 wickets only fall. So in an over, chances of wicket not falling are more than the chances of wicket falling. And then okay, one wicket can fall in an over, the chances are more than the chances of two wickets falling. You have to take into account all these relationships while building a model for complex experiments. So we saw that there are many experiments where defining multiple random variables, understanding relations between them, trying to model distributions and between these random variables is of great use. What you are saying ki this, there is a relation between x and y. We have defined multiple random variables. There is a relation between x and y. Wickets and more wickets are falling in an over, then the runs will be scored in that over, which are generally less. unless it may be a last over or something like that, or some good player comes and starts cheating. In the next section, we will see the person is informed. We'll see the objects that will focus on when we want to jointly study multiple random variables. Two random variables, joint marginal conditional PMFs. So what we are saying, there are only two random variables. We will start with two random variables and eventually we will move to multiple random variables. We have defined the PMF of one discrete random variable, but when we have two discrete random variables defined in the same probability space, many PMFs can be defined. Okay, we have joint PMF, marginal PMF and conditional PMF. Okay, what is saying, in one RV there was only one PMF of the, but if there are two random variables or two or more, then we can have marginal PMF, joint PMF and conditional PMF. Okay, we will see their products. Suppose x and y are discrete random variables defined in the same probability space. Let the range of x and y be tx and ty respectively. The joint PMF of x and y denoted by fxy. F subscript xy is joint PMF. Joint PMF, probability mass function. And the ranges of x and y is from its tx, the range is ty. This function fxy is defined as ptx into ty to 0, 1. This is the codomain, this is the domain. This can take values, this fxy can take values in tx and ty, any value which belongs to tx and ty, but the range, or here the codomain or range, is 0 to 1 of that function. Why? Because this is a probability mass function, and we know that for a function to be a probability mass function, it should be greater than equal to 0 and its sum total shall be 1, not more than 1. Sum total of all the possible values in the sample space. Okay. Now joint PMF can be written in the form of a table of a matrix. If two random variables hai, we'll make a table, and this can be written like this. We'll take one variable, second variable here, what is the range of x, what is the range of y. So joint variable will be fxy here, in which fxy, this will be t1, t2, t3 up to tx, t1, t2, t3 up to ty. इसको t dash कर देते हैं because this t1 cannot be equal to t1. So this will be t1 dash. Similarly this one, this will be t2, this will be t2, t1 dash t. Similarly we'll get the, and all this sum will be equal to 1, and this all will be greater than 0. This is what he is saying. toss a fair coin twice. Suppose a fair coin is tossed twice independently, and we will define the random variable xi as मतलब the value of the random variable will be head, will be 1 when it's a head, and will be 0 when it's a tail. What we are saying, we have got it is x1 and x2. So we can define a table. Let's make a table. x1, x2. x1 has got two values, 0 and 1. x2 has got two values, 0 and 1. Define either it's a tail, head, head. Now both are tails, 0, 0. This will be f x y, or let's not do x1. Chalo. So if we will write f x1 x2, told you x1 x2 is 0, 0. This is probability of x1 intersection x2. This value of p x1 to p x2, because independent events. इसमें को p of x1 and x2 can say. Independent events. Probability of x1 is half into half. This will be 1 by 4. 1 by 4. Similarly, this will be f x1 x2 when x1 is 1 and x2 is 0. Okay. Similarly, this will be x1 when x1 is 0, x2 is 0. Be half into half. Same type of probability, 1 by 4, 1 by 4, 1 by 4. If you add this is greater than 0, this is greater than 0. And if we add this, it's equal to 1. So this is the joint probability of x1 and PMF of joint. To generalize this, suppose you have two random variables, x1 and x2. You put all the values taken by x1 in the first row of the table and all the values taken by x2 in the first column of the table. The ijth position in the matrix will give the probability that x1 taking the value of y and x2 taking the value of j. It's same now. I, j. Okay. A two-digit number from 00 to 99 is selected at random. Let x be a digit in unit place. Let y be the remainder obtained when the number is divided by 4. We have seen this example. x की range है 0 to 9. y की range है 0, 1, 2, 3. तो अगर हम जॉइंट PMF निकालना चालू करते हैं इसका x 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. ओके. और y की वैल्यू है 0, 1, 2, 3. पहला निकालते हैं. ऐसा नंबर जो 0 से 0 भी हो एंड बेसिकली व्हाट इज हैपनिंग, एफ एक्स वाई, ये वाई है ना, एक्स वाई 0,0 चाहिए हमको. देन वी आर सेइंग दैट दिस इज प्रोबेबिलिटी ऑफ एक्स इक्वल टू 0 and probability of y equal to 0. Together they are happening, means there will be an intersection. Now intersection, we can multiply the probability x equal to 0 into p of y equal to 0, as they are independent. No, to leave it at that. So this probability now we can find by logic and not by the formula. They are both intersection. See 0. How many numbers? If 0 is divided by 4, and do 10 is divided by 4? No. But 20 is, 30 is not. 40 is, 60, 80, yes, 1, 2, 3, 4, 5. We got 5 numbers. And how many are the total numbers? 100 numbers. This value is 1 by 20. Now I want to just say p of x equal to 0, which we have seen earlier was 1 by 10, and this was 1 by 4, I think, है ना. This is 1 by 4. This is not equal to this, so they are not independent. Similarly, what will happen, we will do everything. If e1 and remainder is 0, so it will be 0, this will be 0, this will be 0. When unit digit is an odd number, it will not be divided by 4, means because we want 0 here, remainder as 0, so it will not be divided by 4, so this odd number we can do easily as 0. And similarly, if it is 0, we cannot get a remainder as 1. Okay, like 10 we can get a remainder as 2, so we'll do it afterwards. First we'll complete this. Now the unit digit is 2 and the remainder is 0. So what is the first number with unit digit 2? 2, no. 0, 2, no. The remainder is 2, not 0. Then 12, yes, okay, we get 12. Then we get 22, no, it is, the remainder is not 0. 32 was divided by 4. Similarly, 52 is divided by 4. 72 and 92. We again get 5 numbers. So it will be similar to this, 1 by 20. Similarly, with remainder 4, we'll get 5 numbers, 1 by 20, 1 by 20, 1 by 20. Now if the, say, x is 0, so we'll do it. Now again x is 0 and y is 1, remainder is 1. I think this will be 0, will not get any number of that. So we can get a number, I think it's 21, but x is 0 now. Okay, no, we will not get. What are the numbers with x 0? 10, 20, 30, 40. We'll always get 2 as a remainder, or it will be divided by 2. So this will be 0. So now x is 1 and remainder is 1. So 0, 1, 11 नहीं, 21, 31, 51, 71, 91, 1, 2, 3, 4, 5, 6, not 31, 5. So 1 by 20, 1 by 20. Similarly, we can fill it everywhere. So there will be 20, I think. Here 20, 1 by 20, 1 by 20, 1 by 20. Here. So we'll get 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 5 into 4 at 20 into 1 by 20 equal to 1. Sum is 1. Okay. Are getting slightly more, we can notice that things are getting slightly more complex, and as we go more and more into complex outcomes, this kind of dependency is very crucial and it will become more and more complicated to write down. We'll stop here with the first part of joint PMF, and the next section we'll look at marginal PMF. Okay, we've done joint PMF, so I'll close this now. I'll get